Good morning, everyone. Let us continue the last session. That is, we are discussing about the uninformed search strategies, and we also discussed about depth first search algorithm. In this session, let us discuss the another important algorithm of this uninformed search, that is breadth first search, or simply we can also call it as a BFS. So it is another search algorithm in AI which travels breadth-wise to search the goal in a tree. So it begins searching from the root node and expands the successor node before expanding it further expands along breadth-wise and traverses those nodes rather than searching depth-wise. Whereas in DFS, depth-wise, we are going to search for a goal node. Instead of depth-wise, it is going to search for along with breadth-wise. So let us discuss this BFS with the help of one example. So see here, this is one example of breadth first search. So how it is going to traverse? So this example of BFS algorithm, it starts from the root node A and then travels to the node B. And till this step, it is same like depth first search. But here instead of expanding the child of B, as in the case of depth first search, here we expand the other child of A, that is node C. Why? Because this is not depth first search, it is the breadth first search. And then move to the next level and traverse from D to G and then H to K. So here, to traverse here, of course, we are considering the lexicographical order. But here the thing is, once this is the root node, so suppose let us say our goal node is J or K. First, it will visit B. After B, it is not going to expand this B. If you expand B, again we are going to get DRE. The expansion of B node, again it will refers to the DFS algorithm. But it is breadth first search algorithm. That means it will go level wise. Level wise. That means in the coming, let us say that this is the 0th level. This is the first level. This is the second level. So first level we traversed A. We came to the level 1. After traversing 0th level, when we comes to the level 1, first it will traverse all the nodes in level 1. That is A to B, B to C. We have finished the level 1. Then we come to the level 2. And then from C, we are going to, as we are following the lexicographical order, from C it is going to visit D, D to E, E to F, and F to G. Suppose if G is our goal node, there itself the algorithm stops the process. But as we are saying, let us say suppose K is our goal node. Now level 2 we have finished. Now we will go for search for process of level 3. So from G it is going to visit the H, from H to I and I to J, then from J to E. That is level wise. It is going to visit all the nodes and the process will continue until we reach to the goal node. So this is what the breadth first search algorithm. And the here important points to remember about this BFS is, the first point is we know that it is uninformed search algorithm, same like DFS. But here we are going to use a data structure of before, that is Q data structure, first in, first out data structure we are following. And coming to the visiting of nodes, it is going to visit the shallowest node, not the deepest node, shallowest node. And whether it gives a complete solution or not, yes, of course, it is going to give us a complete solution. It's not like DFS, not incomplete, it is complete. And it gives us the optimal solution. When we ask the same question for DFS, it doesn't give the optimal solution, but whereas coming to the BFS, it gives us the optimal solution. So coming to this advantages, the same thing. BFS will provide a solution. If there exists, definitely it will give us a solution. And if there is more than one solution for a given problem, then BFS will provide the minimal solution. That is, it gives us the optimal solution, which requires the least number of steps. Coming to the disadvantages, it requires lot of memory. Why? Because each level of the tree must be saved into the memory to expand to the next level. For expanding the next level, the before level, it is going to store it in the memory. So that's why it requires lot of memory. And similarly, it also requires lot of time if the solution is a little bit far away from the root node. So these are the two advantages. And coming to the conclusion, as I said, it requires a lot of memory space and time consuming, and it uses a FIFO-Q data structure for implementation. Complete? Yes, it is complete. And coming to the time complexity, same like the one that is order of B power D, where B is the branching factor and D is the depth of the tree. Similarly, space complexity is also order of B power D. Optimal? Yes, it is going to give us a optimal cost. If step cost equal to 1, that is no cost. All step costs are same. And one more way to find is order of vertices plus edges. In these two ways, we can find out the time complexity and space complexity of this breadth first search algorithm. Now, another type of uninformed search is uniform cost search algorithm. As the name itself indicates, this uniform cost search algorithm, we are going to include the cumulative cost to expand each node from root node to the goal node. It does not go depth or breadth. It just searches for the next node with the lowest cost. That's it. And let us discuss with this one simple example. See, this is the one of the given graph, and S is the start state and G is the goal state. Now, with the help of uniform cost search, we have to we have to traverse from start state to goal state. So let us start from here. And if we follow the lexicographical order, when we expand the node S, we have two possibilities that it can go for A, it can go for G. If directly it goes to G, yes, obviously it will reach to the goal state. But as the name itself indicates that it is uniform cost search, okay, it will go with the least cost. So when we see 1 and 12, 1 is the least cost. So obviously it expands node A and it reaches to the node A. And coming to this node A, again it expands, when it expands A, we can traverse to node B and node C. But node C is having the least cost, so it will reach us to the C. And coming to the C, it expands. We can reach to node D and node G. Here also from node C, directly we can reach to the goal state. But as it sees the cost, so 1 is the least cost, so it will reach to the D. After reaching to the D state, there is no other option, and if we expand the node D, we are going to reach to the goal state, that is G. So this is what but here even though we traverse this way, our total cost from S to G is just 6. You can see 1 plus 1, 2, 3, 3 plus 3, 6. And if we directly go, there is 12. That is 6 is very less compared to 12. Okay. Even then we travel that much, we got the very least cost. Okay. So the advantage is it gives you the optimal, because at every state it is going to consider the path with the least cost. But the disadvantage is it does not care about the number of steps involved in searching, as we seen in the previous example, only concerned about the path cost. So due to this, which the algorithm may stuck in an infinite loop. Yes, is it complete? Yes, it is complete. And the time complexity is order of B power C/A. It is the where epsilon, we can say that it is the lowest cost and it is the optimal cost. Similarly, the space complexity also order of B power C/epsilon. In this way, we are going to find out the time complexity and space complexity. Optimal, yes, it is going to give us the optimal solution. Then, depth limited search algorithms. It is similar to DFS, but with a predefined limit. That is, and it can, this depth limited search can be terminated with two conditions of failure. That is, if it indicates that the problem does not have any solution, it may fail. And if it defines no solution, there will be some depth limit will be there. Till that depth limit, if you don't find the solution, it is going to fail. That is cutoff failure or standard failure. And the advantage is memory efficient, and it has incompleteness, and it may not be optimal. It means it does not give us the optimal solution. So we can see that this one at level 0, then depth wise it will travel level wise and depth wise to some depth level. If we find the solution, okay, fine, it is gives us solution. Otherwise, it doesn't give the solution. And then next one is iterative deepening depth first search. This iterative deepening is a combination of DFS and BFS algorithms. That means find out the best depth limit and gradually increasing the limit until a goal is found. Okay. So up to a certain depth limit, it will find, and then after it is going to keep on increasing the depth limit after each iteration until the goal node is found. So it combines both the benefits of BFS fast search and DFS memory efficiency. So this is one important point: BFS fast search and DFS memory efficient. And see here. So this is one example of this iterative deepening DFS. So at level 0, it will search for node A. Coming to the second iteration, A, B, C, it will traverse. And coming to the third iteration, A, B, C, D, you can see D, E, then it goes to C, then F, then G. And when here, if we find the goal, there itself it starts, stop the right. And if it is not, this is the goal node. Let us say that K is the goal node. Then it will traverse C, A, B, D, H, then I, then E, then C, then F, then K, then in this way also it is going to find out the solution. And that itself is the drawback of this. That is, it repeats all the work of the previous phases. Means in each iteration, every time it will traverse the already visited nodes. That itself is the disadvantage of this iterative deepening depth first search algorithm. So you can see here, each iteration we are visiting the same already visited nodes. Then bidirectional search algorithm. So as the name itself indicates, it runs two simultaneous search. That is, one from initial state called as the forward search and other from the goal node called as the backward search to find the goal node. So it replaces one single search graph with two small subgraphs in which one starts the search from an initial vertex and parallelly other starts from the goal vertex. The search stops when these two graphs intersect each other. And this bidirectional search use search techniques such as breadth first search, depth first search, and depth limit search. Coming to the advantages, it is fast, it requires less memory. But coming to the implementation of bidirectional search is difficult. Why? Because parallelly we have to start from the goal node and the start node. And in bidirectional search, there is one limit that one should know the goal state in advance. Then only we can implement this bidirectional search algorithm. So see here, this is one of example. So bidirectional search, if we apply for this this algorithm divides this one graph it into two subgraphs. It starts traversing from node 1 in the forward direction, and then from the goal node, that is 16, in the backward direction. And this algorithm terminates at node 9 when two searches meet here. So in this way, this bidirectional search algorithm works. So this is all about the uninformed search algorithms, where we discussed about DFS, BFS, depth limited search, iterative deepening depth first search algorithm, and uniform cost search. And the last one is the bidirectional search algorithm. So these are the 6 algorithms that comes under uninformed search algorithms. And in the next class, we discuss about the informed search algorithms. Thank you.